Good day, students. Today we are in the 12th lecture for the laboratory course Fibre and Yarn Quality Evaluation, and for the and common for the theory course Textile Quality Evaluation. Today we will look into the topic determination of bundle fiber strength testing, which is the fourth experiment in the laboratory. Also, it is a part of the theory course. So we have already seen the tensile testing for fiber strength, yarn strength, and fabric strength. So for fiber strength, there is single fiber strength and bundle fiber strength are available. For yarn, skein, single yarn, and yarn impact. For fabric, test strip, ravel strip, and graph test. For the fiber testing, single fiber strength, CRE type instrument, universal tensile tester is used with the fiber jaws common for synthetic fibers. And for bundle fiber strength, you have Stelometer, Presley tester, inclined plane tester, and HVA instrument. So in this experiment is concerned with the Stelometer. The fourth experiment is the determination of fiber bundle strength testing using Stelometer. The aim of the instrument is to determine the cotton fiber bundle strength using Stelometer. So what is Stelometer? As we know, strength and elongation has to be found out for the fiber bundle. The instrument is named after strength ST, the letters S and T for the strength testing, and for elongation testing ELO is used. So the instrument is named as Stelometer, strength elongation meter, or Stelometer is the instrument used for testing. So we need not forget it is simple. Strength and elongation testing of bundle fiber is done using Stelometer. So you can measure strength as well as elongation using this instrument. So the standards that are followed for testing in this instrument is Indian Standards 3675. Method of determination of bundle strength, that is tenacity, is the term used for or that is the term that you have to find out of this experiment. You have already known the definition for tenacity. It is specific stress at break, and it is done for cotton fibers. The another standard also available for fiber bundle strength testing is ASTM D1445. Standard test method for breaking strength and elongation of cotton fibers, flat bundle method. The bundle of fibers that are used are in a flat form, so it is called as flat bundle method. The principle behind Stelometer is constant rate of loading. That is, for every the change in time, the change in loading remains constant, and it is the loading that is maintained is 1 kg per second. This is the constant rate of loading that is maintained in this experiment. The increase or rate of increase of load is uniform with time, or loading rate is constant. That is why it is called as constant rate of loading, CRL. Whereas the rate of extension is dependent on the load elongation characteristics. The rate of extension is not constant, and it depends upon the load elongation characteristic of the material. So the fiber may exhibit different fibers will exhibit different extension types. So accordingly, the rate of extension will change from start to end, and it will not remain constant. This is a picture of Stelometer instrument available in the laboratory. The manufacturer is MAG. So this is one instrument. One more instrument is also available, which is the manufacturer of this instrument. This is also Stelometer. A slightly different appearance. The manufacturer is Statex. One more instrument. This is also a Stelometer. The Icon Industries are the manufacturers of this instrument. These three instruments are available in our laboratory. We have seen the pictures of the 3 instruments that are available in the laboratory. Now let us go into the accessories that are available along with the instrument. The first 3 accessories are coarse comb, fine comb, and tweezers. These are the pair of combs, one fine and other coarse comb, which is used to comb the fibers. That is the preparation. This is the tweezer used to pull the flat fiber bundle from the comb. This is the tweezer. This is the fiber in the tweezer. The other accessories are specimen clamps. The specimen clamps are common for the Priestley tester. It is actually manufactured for the Priestley tester, and the same clamp is used in the Stelometer instrument also. This clamp may have an insert in between. If the insert is there, then the gauge length or the length of total length of fiber that is available for the test is 15 mm. If the insert is removed, then it is 11 mm. The 11 mm length of fiber is used. Both these gauge lengths are used in Stelometer. The common gauge length that is used for fiber testing is 15 mm. If the fibers are very sticky and slippery, if the honeydew content of the cotton fibers is very high, then you may have to go for 0 gauge length. Or if the fibers are very short, then you have to go for a 11 mm gauge length without the insert in between the 2 jaws. The 2 jaws will be there and there will be an insert. If you take out that insert, then the 2 jaws alone can be placed in the clamp wise. The next part is the clamp wise. That is the setup that is available for placing the jaws and tightening of fibers, placing the fibers, tightening, all those things. For tightening, a wrench is used, and for cutting the edges, the shear knife is used. This is the clamping wise, the total setup. The jaws, the 2 jaws are placed in the clamping wise. You can see the space between the 2 jaws, the space between the 2 jaws with an insert. So the total length is 15 mm. The fiber length, that is the total length of the fiber, will be 15 mm. This fibers are placed in these clamps and the clamps are locked and they are tightened using the vise. And the tweezer is removed and the bunch is taken, and using the knife the extra edges of the fiber are cut so that there is a 15 mm length. Now let us draw the diagram of the instrument. This is the pendulum. You can see the shape of the pendulum. Next is the beam. See, the green color is the beam. The beam is behind the pendulum, so it is given in the dotted lines. So they are pivoted at this point. So there is a joining like this for the pendulum and the beam at this place. There is a pivot. So the pendulum beam, pendulum red color, beam is in green color. So there are 2 jaws, J1 and J2. Jaw J1 is held in the, you can place the jaw in the beam. There is a holder which holds the jaw J1, and there is a holder in the pendulum which holds the jaw J2. So you can place the jaws together in the in its position. If there is a gap like this, then it is 15 mm gauge length. If there is no gap in between these two, then it is 0 gauge length. So jaw J1 and J2 are to be mounted on one on the pendulum and the other on the beam. So here the fiber bundle is placed. You cannot place it directly here. we have already seen the jaws are usually kept in the clamping wise, and the fibers are placed, locked, tightened, and the edges are cut using the knives, and only then it is placed here. This is the back side of the instrument. You can see the pendulum here. This is the pendulum. This one. This is the beam. This one is the beam. The left side is the beam. This right side is the pendulum. In the diagram which we have seen earlier, we saw the pendulum on the left hand side and the beam on the right hand side, because we are drawing the front view of the instrument. This is the back view, hence it is reversed. Then here you have the two jaws where you can place the two jaws. One jaw is held to the beam and the other jaw is held to the pendulum. This is the dashpot used to adjust this. By adjusting this place, you can adjust the speed of the instrument. The speed or the loading rate is said to be 1 kg per second. And here you can see the catch, which you can see on the front hand side also. The fibers are mounted onto the jaws separately before placing it in the position in the pendulum and the beam. So this is the picture which we saw already. This is the preparation of the fibers or the clamps before placing it for testing. The fibers are placed in the clamps and it is tightened, and only then it is placed in the in between the in the jaw holders. One jaw holder on the beam and other jaw holder on the pendulum. Before mounting, the fiber sample is placed in the jaws and then mounted onto the jaw holders in the pendulum and beam. Let us come back to the diagram. So this jaw holders with the fiber is prepared before and then mounted here. Now this beam is the center of gravity of this beam is not with the center of gravity of the pendulum. The center of gravity is away from the center actually. That is why it will not stand straight. When you release, there will be a clamp here. If you release that, it will move like this. So the center of gravity is away. So it is the center of gravity of the beam is away. It is away and is such that the beam and the pendulum is in vertical. Both are in the vertical position. It is and if you release the beam, then it will start rotating clockwise. The center of gravity of the pendulum is here. The center of gravity of the beam is here. Both are in vertical position at the start. When you release, then the beam, which is heavy, will move in the clockwise direction as its center of gravity is away. This is the fulcrum O, where the beam and the pendulum are held together. If this fulcrum is not there, then the movement of the beam will not cause any movement of the pendulum. Then here, this is already seen the center of gravity of the pendulum. This is the center of gravity of the beam, which is away. This arrow mark is given because it will move clockwise. Only there it is stable. There is a stop available to stop the movement of the beam at the end point. As already mentioned, the beam and the pendulum are in vertical position at the start, and when the catch is released, the whole assembly rotates clockwise. The fulcrum is at O. So this is how it rotates when the catch is released or when the trigger is given. This is how the setup moves. This is a line diagram. This is the pendulum, the red line. This is the fiber. On the fiber, the force exerted F is in this direction, and this is O. So this is a line diagram. We'll see later this for understanding the principle behind the measurement. The loading of the fiber is by this pendulum system. As the beam rotates, the pendulum moves. The pendulum's movement is because the beam moves. Because the pendulum is stable, but the beam is not stable because its center of gravity is away. So this beam moves, and this the fire this there is a jaw which is held in the beam, and there is a jaw which is held in the pendulum. This setup moves because the beam pulls the pendulum via this fiber. The load is transferred along this fiber. So this type of setup eliminates the inertial errors because of the weight. If the weight has to be moved in the opposite direction, then because of the weight will give some resistance. That inertial errors are avoided in this instrument. These inertial errors are present in CRT type instruments, whereas in this instrument that inertial errors are avoided. So this there is a dashboard here. You can see a dashboard. This dashboard is used for adjusting the speed of the instrument, or the loading rate is adjusted using this pendulum. I'm sorry, this dashboard. There is a screw on the dashboard which is used for setting the loading rate at 1 kg per second. This is the back side of the instrument. This is the beam. This is the pendulum. This is the fulcrum. This is the dashboard. There is oil here for smooth movement of the beam. And this, by adjusting the screw, you can adjust the speed or the loading rate. The loading rate can be set to 1 kg per second by adjusting this. You can see the movement now released. The clamp is released, and you can see the movement here. Before continuing with the instrument description and drawing the diagram, I thought that the calibration of the instrument has to be told at this point. The instrument has to be leveled before starting the experiment. The leveling of the instrument is done by adjusting a screw near the spirit level at the bottom, and seeing to that the spirit level is in position. That is, a bubble will be in between the two lines that are specified. After leveling, the loading rate has to be set up. For adjusting the loading rate, we have seen how to place the fibers in the fiber clamp. Instead of placing the fibers, a thin metal strip is kept in place. You need not cut that. It is not a difficult task. A thin metal strip is placed in the fiber clamps at where you place the fibers. Instead of that, a metal strip is placed and locked using the vise in the clamping area, and then the jaws are taken and clamped in the jaw holders in the jaws. One jaw holder in the beam and the other jaw holder in the pendulum, as we have seen already. The pendulum is released by depressing the release trigger, or the catch is released, and the loading scale is noted and seen to that when it goes from 0 to 7, it takes 7 seconds, which means for 7 kg it is 7 seconds, and that is 1 kg per second. So this is the loading rate set up in the instrument. That speed, that calibration is done by the dashpot, the screw in the dashpot as shown earlier. I have told you we have to check during calibration. This scale has to be noted. The loading rate has to be noted in this scale. For 7 seconds, it should move till 7 kgs. I have shown only till 6 kgs. it is actually till 8 kgs in the instrument. 1 to 7 kgs are the apt ones. So this is the loading scale. This is the pointer for the load scale. So P1 is the pointer for the load scale. Next is the elongation scale. This elongation scale, the pointer is P2, in which you can measure the elongation of the fiber. This is loading scale for measuring load, elongation scale for measuring the elongation. There is an attachment between with the pointer of the load scale and the elongation scale. The elongation measured in percentage, load scale is in kgs. This is the load scale in the instrument and this is the elongation scale. The load scale pointer is here, the elongation scale pointer is here. Here the elongation scale moves and the pointer is attached to this load scale so that the exact elongation is measured. The elongation scale moves, load pointer moves. Load scale remains constant, whereas the and this pointer and the elongation scale both move to record the exact elongation in the specimen. There is a sensing pin here. The sensing pin stops when there is the difference between movement of the beam and the pendulum. When the sample breaks, the sensing pin senses by the change in the movement of the beam and the pendulum and stops the loading scale from movement. The beam and the pendulum continues movement even after the fiber bundle breaks, but the pointer stops moving. P1 pointer stops moving because the sensing pin moves away the movement of the pointer. This ensures that the maximum reading is recorded on the load scale and in the elongation scale the maximum elongation. This is how it actually moves, and there will be a difference which is sensed by this sensing pin. This clockwise movement will be happening. Now let us look into the total instrument and how the experiment is done in this instrument along with the slide description of the instrument. This is the Stelometer and this is the left side is the torsion balance. Instead of this torsion balance, we can use micro balance. This is a close look of the Stelometer. This is the elongation scale. This is the load scale. This is what you can see in the front of the instrument. And then you can see here there is an arrangement for the placement of the jaws J1 and J2. This is what you can see in the front. And in the bottom you can see a catch which is used to start the used to release the beam. Now let us see the preparation of the sample. The fibers using the two combs, the cotton fibers are combed in this manner. Then using the tweezer, the sample is pulled from the combs in this manner and the prepared sample is kept on the holder. Notice that the holder is here. See, the adjustment is done using the thumb at the bottom and at the top the other fingers are there. This is how you have to place. Now the tweezer is pulled down and the jaw holders are closed. These are the two jaws and in the jaw holders the fiber is kept and these two nuts are locked tightened. It is tightened here and the nuts are locked. Using this, the nut is locked. This is the end point. This is the end point. Now the tweezer can be removed and the jaws can be pulled out and the extra fibers at the ends are cut. The extra fibers at the ends is ensured that they are cut. These are the two jaws. Now the movement of the beam and the pendulum was there after the uh, movement, after the break of the fiber also. But the load scale has stopped and the elongation scale also stopped after the fiber sample has been broken. This is the load scale and this is the elongation scale. As I already mentioned, the elongation scale will be moving, whereas for the load, the pointer will be moving. This is the pointer for the load scale and this is the pointer for the elongation scale. So now the reading for the load is 3.3 kgs and for elongation it is in between 0 to 10. It is 1, 2, 3, 4. It is 4% elongation. Okay, so this pointer is attached along with the load scale and the elongation scale moves here. The elongation scale reading and the load reading has to be noted in the tabular column. The load reading we found was 3.3 kgs, which is nothing but the bundle strength, that is in kgs. The elongation was 4%. So those have to be noted in this tabular column. Next, we have to find the bundle weight and the breaking tenacity. The breaking tenacity has to be calculated using bundle strength and bundle weight using a formula, whereas bundle weight has to be found using the experiment. The bundle that has been broken has to be weighed. After performing the experiment, we'll see how the bundle is weighed. Actually, the jaws are taken, opened, the fiber bundles are taken and weighed using a microbalance or a torsion balance. Now the jaws have to be removed from the jaw holder like this. Place the jaw holders in the sample preparation area. Loosen the nut as it was tightened. After unscrewing the fiber clamps, you can see the fibers here on the jaws. Here you can see those fibers. These fibers have to be removed and weighed. See, you have the forceps for removing the fibers. The removed fibers can be weighed in the torsion balance that is available in the laboratory, which is a very old instrument. Or we can weigh that in the weighing balance, micro balance that is available in our laboratory. We usually use micro balance to weigh the fiber bundle after testing. The bundle weight measured using the electronic balance is entered here in the tabular column. Bundle weight in milligrams. And now next we have to calculate the breaking tenacity in gram per tex. Breaking tenacity, we have used 15 mm gauge length now. The formula to find breaking tenacity in gram per text is breaking load in kgs into 15 divided by bundle weight in milligram. Substituting for the breaking load, which is 3.3 kgs, 15 is the constant and 2.3 is the bundle weight. Hope you have found the answer. Yes, it is 21.52 gram per text is the tenacity. The calculated bundle tenacity is entered in the tabular column like this. And similarly, you have to take many more readings, at least 15 readings for a single sample. If the bundle strength is less than 3.3 kgs or if the bundle weight is less than 2 gram, it is better to repeat the experiment. This is the formula used for finding the breaking tenacity if the gauge length is 11.8 mm. Usually this is called as 0 gauge length and 15 mm is called as 1 by 8 inch gauge length because the strip with this 3 mm or 1 by 8 inch for 15 mm gauge length and the strip is taken off and it is there is no distance between the two jaws, so it is called as 0 gauge length. But the length of the fiber is 11.81. This is the formula for finding if the gauge length is, if the fiber length is 11.8 mm or the gauge length is 0. These are the final results that are to be presented after tabulating 15 readings for a single gauge length and then taking the average of the 15 readings. It is corrected to 1 decimal place and recorded here, and the average elongation also similarly is recorded here. We have to mention the instrument. Stelometer is the instrument used here and the gauge length is 15. Similarly, it can be measured for 0 gauge length also if required. Let us now try to understand how this angular movement of the pendulum is measured as the load reading. We'll see the derivation for that. So this is the pendulum, the red color line we have already seen, and jaw J1 and J2, and the pink color is the fiber bundle. This is the axis of the pendulum. Now we have the fiber. F is the force acting on the fiber which has to be measured. The force is acting at the point Q, which is at the distance of OQ from the center. This force has to be balanced by the force on the other direction, that is the weight of the pendulum. So G, at the point G, the weight of the pendulum acts. The pendulum makes an axis angle theta with its axis. So this is the angle theta. So this is a right angle triangle and the distance OG sine theta is the distance from the center where the weight W acts. So there is a moment on the left hand side and there is a moment on the right hand side. That is clockwise moment, and the left hand side, it is the anti-clockwise moment. In this right angle triangle, this distance is OG sine theta. It is found out from this right angle triangle. Now, by law of moments, the clockwise moments will be balanced by the anti-clockwise moments. This left side is the anti-clockwise and the right side is the clockwise moment. So clockwise moment is F into the perpendicular distance, which is OQ, and on the left hand side it is the anti-clockwise moment, which is W, and the perpendicular distance is OG sine theta. So from this, F is equal to W into OG sine theta divided by OQ. From this, W is a constant weight of the pendulum, OG the distance, this distance, and the OQ distance are constants. So removing the constants, we introduce the proportionality sign. So F is proportional to sine theta. That is why the force acting on the fiber is measured by the angular movement of the pendulum. The angular movement of the pendulum, in introducing these constants, are given to the load scale or the pointer of the load scale. The movement of the pointer of the load scale is a measure of the theta and the calibration is done for these constants in the load scale. This is how F is proportional to sine theta.